Greetings and welcome back. In our continuing evaluation of NMR and what this can tell us about our molecule, we're going to be looking today at the number of environments and also the integrals. So we'll start off with an example molecule, which is this ketone right here. Of course, in NMR what we're looking at is the hydrogens. Therefore, I would highly suggest you draw these out as Lewis structures. I know that it's boring, I know that it takes time, but it's really important to be able to see all of the hydrogens. So I'm going to do that right now. I would suggest that you guys all do the same for any molecule that you're looking at by NMR. Just to make sure you get all of your hydrogens. Alright, that one's a little tiny hydrogen. Okay, so looking at this molecule, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different hydrogens. The first thing that I really want to worry about and focus on is the number of different peaks, or the number of different environments. Remember that on an NMR spectrum, we see by chemical shift, we see a number of peaks corresponding to the number of different hydrogens, or hydrogen environments that we have. So what about this one right here compared to this little skinny one right here? Well, those hydrogens, we might classify them the same. They don't know that they're the same thing. They don't know that they're in the same environment. But if we look at each one individually, let's look at the top one. That is a hydrogen which is bound to a CH2 and then a C double bond O. This is a hydrogen that's bound to a CH2 and then a C double bond O. And moving on from the C double bond O, of course, they both have that isopropyl group following. Therefore, those hydrogens are in the exact same environment. They have the same amount of shielding. They have the same amount of electron density being pulled away from them. Therefore, they give you the exact same peak. If you compare them to the third hydrogen on that same carbon, it's in the exact same situation. It has the exact same amount of shielding. It's a hydrogen that's bound to a CH2, bound to a carbonyl, followed by an isopropyl group. Therefore, all three of these hydrogens would be in the exact same environment. And instead of circling them individually, you could circle all three of these guys the same. So let's just say that these guys are together in environment A. They, of course, don't know any better. They're just a peak. If we look at it, it's a CH3 that's next to a carbonyl, so that probably appears somewhere around 2 to 2.5. I'm going to say 2.1 ppm. All right, but again, those hydrogens don't know each other, so if we think about where they're going to appear, one's going to appear right here at 2.1. The second one's going to appear right on top of it at 2.1. The third one's going to be exactly the same. So basically you have three peaks that appear exactly on top of each other. That might seem silly, but it'll be very important. We'll get to that shortly. All right, moving on down the molecule, we have a hydrogen right here. That hydrogen is attached to a carbon next to a carbonyl. Just like these guys, they're a hydrogen attached to a carbon next to a carbonyl. However, this environment is different than that environment. This is a hydrogen attached to a carbon with two methyl groups. This is a hydrogen attached to a carbon with two hydrogens. Any slight, even if it's minuscule, any slight differences in their neighbors or their neighbors' neighbors is going to give you a slightly different shielding environment. Therefore, it'll show up at a slightly different place in our NMR. In fact, for this environment, which I will call environment B, it's going to show up a little bit further to the left because it's got more methyl groups around it. It's got a little bit more business about it. So I'm going to guess that this guy's going to show up around 2.4 ppm. But the point remains, it's slightly different than environment A. However, this guy only has one hydrogen, so it's just going to have one peak. There's going to be nothing stacking on top of that guy because that guy's all by himself. All right, moving on to this bottom carbon. I've got three hydrogens here, and I probably don't need to convince you that they're all going to be the same. So these are hydrogens next to a carbon with two hydrogens, next to a carbon with one hydrogen, that's next to a carbonyl. All right, so you can count those out and think about this the same way that we tracked out hydrogens when trying to figure out E or Z, or trying to figure out R and S, and we ranked them. But instead, just kind of walk their pathway and see how far they are away from things. If you examine all three of these, you would find that all three of them are exactly the same. So I'm going to say that these guys are in environment C. Despite the fact that all three of these hydrogens are on a carbon, they're all on a methyl group together, they're not the same as this one off to the right. This one is a methyl group that's directly attached to a carbonyl. This one's a methyl group that's directly attached to a CH that's attached to a carbonyl. So let's move on to these three hydrogens on the left side. So what about these guys? These are hydrogens that are attached to a carbon next to a CH next to a carbonyl, which is exactly the same as these three hydrogens, which were attached to a carbon next to a CH next to a carbonyl. In fact, if we walk them down together, oh, it'll let me do this. We've got three hydrogens on each of these that are next to the same CH that are next to the same carbonyl next to the same CH3. Ooh. So therefore, what's going to happen is all six of these hydrogens, 1, 2, 3, 4, 5, 6, they're all going to be in exactly the same environment. They, of course, don't know each other. They don't look at each other and say, hey, you guys are the same as me. But they are the exact same distance from the exact same identity molecules. So they're all CH3s next to the same CH. Right? So we've got CH3s next to the same CH, next to the same carbonyl, next to the same CH3. Therefore, while these two CH3s are identical as each other, they're not the same as this guy off to the right. Now, how many hydrogens are going to be in this environment C? Well, all three of these and all three of these are all going to stack together. That guy's furthest away from everything, so it's probably not going to experience much effect of the carbonyl, but maybe a little bit. So we'll say that these guys are going to be somewhere around 1.3 ppm. That is a guess. It's probably somewhere between 1.3, 1.5, something like that. But we'll put them, they'll be furthest off to the right. So we'll see 1, 2, 3, 4, 5, 6 of them all on top of each other. So what we can take away from this molecule is that it has three different environments, A, B, and C. Our environment A was right here, B was further to the left in terms of a chemical shift, and C was furthest to the right. B was furthest to the left because it had the most de-shielding. It was that guy stuck in the center there. It's next to the carbonyl, and it's also next to a couple carbons. All right, so here's two things we can take away by looking at this spectra. The first is we can tell that there are three discrete environments, A, B, and C. The second is the second thing we can tell is roughly how close are they to something that is shielding them or de-shielding them. But the second new thing that we can do is we can actually get the area under the curve, and that will tell us how many hydrogens are in that environment. Just like the way that we stacked these up, the area under a curve is called an integral. So in calculus you did that with, some curve. You would integrate it to find the area under the curve, which would just be all of this space. We can do the exact same thing with an NMR peak. You don't have to do any calculus though. You just ask the computer to tell you what is this area that's underneath of that peak compared to what is the area that's under this peak right here. And of course, in the way that we've drawn it off to the right there, the more hydrogens that are in the exact same spot, the more area they will be under that curve. Therefore, if the ratio, looking back at this kind of hypothetical one I made in the situation, the area under the curve of this one compared to this one is, let's say, 3 to 1, then you would know that this guy corresponds to a hydrogen environment that has 3 times as many hydrogens as this one. We did the one on the right ourselves, but the area under the curves here would integrate to 1 to 3 to 6. This is incredibly handy because not only do we know where one of these things is in terms of chemical shift. That is to say, roughly what is that hydrogen environment next to. Not only do we know how many different hydrogen environments are in the molecule, but we actually know exactly how many hydrogens are in each environment. It does give you a ratio, so it is of course possible that this could be 2 to 6 to 12. It's just a ratio, but it's an extremely important amount of information, and by the mass you could figure out roughly how many hydrogens are in there. And there's a very big difference between something with 10 hydrogens, which we saw up there, as compared to something with 20 hydrogens. So that's something that we can work out pretty simply. But that ratio is a really important thing for us to be able to get. All right, I'm going to give you one more example. I'll let you try it, and then we'll work through it together. All right, so I'd like you to try with these two molecules to figure out three things. The first is the number of different environments. The second is roughly what you think the chemical shift would be in ppm. Third is, what is the integral of each of those environments? So pause this and give it a try. Don't forget, draw these out as Lewis structures with all of your hydrogens in. Alright, welcome back. What I have done here is drawn out kind of a little bit of a combination between a Lewis structure and a condensed formula. You know that if you have a CH2 or a CH3, that all of those hydrogens will be in the same environment. So I didn't go all the way to Fisher projection here. You can use whatever works best for you. So let's start with the one on the right, which is hopefully obviously a little bit more simple. We have a CH3 on the left. We have an H on the right. Those are, and I don't have to go through this, I'm sure, those are obviously different environments. This will be environment A, and this will be environment B. So you would see two peaks in an NMR. The environment A is a CH3 next to a carbonyl, so we would say that that guy's probably between about 2 and 2.5. I'm going to say that it's around 2.5 just because there's also an oxygen on the other side of that carbonyl. But 2.5-ish. For environment B, that guy is the hydrogen on a carboxylic acid, which is somewhere between 10 and 12 ppm. I'm not even going to bother guessing. Somewhere in that range. All right, so that is the number of environments is 2. We have chemical shifts corresponding to roughly where we expect them to show up. And the last thing to do for now is to look at the integral. The one on the left has 3 hydrogens, which will all be the same, so they'll all stack on top of each other. So the area under the curve here would integrate to 3. So we're going to say that this is 3 H's. And this is always a ratio. Environment B only has 1 H, so that will stack by itself, and it will only integrate to 1 hydrogen. Therefore, the ratio of the areas under the curve, or the integrals, would be 3 to 1. We could draw that out if we wanted to, but really NMR is all about looking at a spectra and trying to figure out what you're seeing. All right, let's go on to the slightly harder one on the left. Here we've got a CH3, another CH3, a CH2, and a third CH3. Starting off to the right, this CH3 we'll call environment A. Obviously this CH2 is not going to be the same as anything else, so that would be environment B. The only thing we have to figure out is those two CH3s off to the left. Are they the same as A? Are they the same as each other? Or are they all by themselves? Well, these are CH3s next to a carbon with a chlorine. This is a CH3 next to a CH2. Therefore, this CH3 and this CH3 are not the same. All right, I'm going to call this one environment C because it's definitely not the same as A or B. If we compare this one down here, the CH3 that we just labeled as C, to the one off to the left, they're both CH3s next to the same carbon. Therefore, they have to be exactly the same as each other. They're CH3s next to a carbon with a chlorine, next to a CH2, next to a CH3. So they are in exactly the same environment. They have the exact same amount of shielding. Therefore, they will both be environment C. All right, to figure out, we could figure out roughly what our chemical shifts will be, but we will have 3 peaks. C is probably going to be somewhere around, I don't know, 1.5 maybe. They're not H's next to a carbon with a chlorine, The carbon with the chlorine is this one right here. If that guy had any H's, they would be in the range of 3 to 4, but it doesn't have any H's, so it's not going to show up. All right, so that one's 1.5. We'll say that this environment B is maybe around 1.7, and A is probably too far away to feel much of anything whatsoever, so it'll be roughly around 1 ppm. These are guesses based on a lot of practice with NMR, but I would be very happy if you said that these guys were somewhere around 1.5, this guy was somewhere around 1.5, and this one was somewhere between 1 and 1.5, roughly. Give or take maybe +2 or +3. All right, what about integrals? Well, this environment C has 6 total hydrogens, 3 on this CH3 and 3 on this CH3. They're all going to stack on top of each other, so they would integrate out to 6 H's. Environment B is a CH2, so it has 2 H's. Environment A has a CH3, so it has 3 H's. So C to B to A is going to integrate out to 6 to 2 to 3. All right, I'm going to give you a couple more problems that I'd like you to try out, and we will go through them first thing in class. Let's do this one, and I'd like you to try that one as well, and we'll go with that. So those will be the first ones we'll go through in class. I'd like you to find the number of different environments, the rough, I would say, to predict the chemical shift, and then also find the ratio of integrals. Thanks very much, and I'll see you soon.